Sean tan amables en ocupar sus lugares. Muy buenos días. El Instituto Politécnico Nacional les da la más cordial bienvenida al Congreso Interpolitécnico de Investigación para alumnos de posgrado 2025. Damos la bienvenida y saludamos con mucho gusto a los integrantes del Presidium, autoridades del Instituto Politécnico Nacional. Saludamos con mucho gusto a la doctora Marta Leticia Vázquez González, secretaria de Investigación y Posgrado. Damos la bienvenida a la maestra Jessica Gasca Castillo, secretaria de Innovación e Integración Social. Al doctor Edmundo Omar Matamoros Hernández, encargado de la Dirección de Difusión de Ciencia y Tecnología del Instituto Politécnico Nacional. A la licenciada Adriana Natividad López Ortiz, jefa de la División de Apoyo al Posgrado. A la maestra Claudia Mirla Padilla Cruz, jefa de la División de Operación y Promoción al Posgrado. Saludamos también a nuestros invitados especiales, funcionarios, directores y directoras de escuelas, centros y unidades, alumnos y alumnas del propio instituto. Sean todos bienvenidos. En estos momentos, la doctora Marta Leticia Vázquez González, secretaria de Investigación y Posgrado, nos complace con el mensaje de bienvenida y nos honrará con la declaratoria inaugural para este congreso. Adelante.
Muy buenos días a todas y todos. Es un honor darles la más cordial bienvenida a la segunda edición del Congreso Interpolitécnico de Investigación para alumnos de posgrado. Un espacio que refleja la vocación del Instituto Politécnico Nacional por impulsar el talento, la innovación y la colaboración científica como motores de transformación para nuestro país. Este año, del 22 al 26 de septiembre, la Dirección de Servicios Empresariales y Transferencia Tecnológica nos acoge gracias al apoyo de la maestra Jessica Gasca Castillo, secretaria de Innovación e Integración Social, a quien agradezco su compromiso por articular puentes entre la ciencia y la sociedad para favorecer la transferencia tecnológica que México necesita. Agradezco también la presencia del doctor Edmundo Omar Matamoros Hernández, director de Difusión de Ciencia y Tecnología, por su valiosa labor en el fomento temprano de vocaciones científicas. En este mismo espíritu, quiero destacar la labor de la Dirección de Posgrado, responsable de la organización de este congreso y pilar en la formación científica de alto nivel, así como de quienes hoy la representan en este presidium. La maestra Claudia Mirla Padilla Cruz, al frente de la División de Operación y Promoción al Posgrado, y la licenciada Adriana Natividad López Ortiz, jefa de la División de Apoyo al Posgrado. El trabajo coordinado de la dirección y sus divisiones garantiza que la oferta académica del Instituto Politécnico Nacional sea pertinente, actualizada y en sintonía con las necesidades del país. Su dedicación y cuidado brinda solidez institucional y fomenta la excelencia académica que distingue a nuestro instituto. Muchas gracias por su labor. La riqueza académica de nuestro instituto se refleja en la diversidad y excelencia de los proyectos presentados. En esta edición del Congreso, más de 430 trabajos de investigación aceptados, provenientes de 48 escuelas y centros de nuestro instituto, además de 35 trabajos que provienen de diversas universidades nacionales. La calidad y relevancia de los trabajos presentados está respaldada por el comité científico que se ha integrado por casi 100 expertas y expertos. Cada trabajo presentado representa un acto de valentía intelectual, creatividad y compromiso con la ciencia de frontera. Son nuestras y nuestros alumnos estudiantes de posgrado quienes protagonizan este esfuerzo, quienes ponen la técnica al servicio de la patria y quienes nos invitan a imaginar los nuevos paradigmas que transformarán el futuro del país. Estoy convencida que esta segunda edición del Congreso reafirma el compromiso de la investigación que se realiza en el Instituto con la apertura de nuevos caminos de colaboración, la creación de espacios de intercambio y el fortalecimiento de las relaciones entre pares, generando oportunidades que enriquecen el desarrollo científico y tecnológico de México. Les invito a vivir estos días con entusiasmo, con espíritu crítico y con la certeza de que cada contribución aquí presentada es una semilla de innovación y una muestra del compromiso con el futuro de nuestro país. Agradezco profundamente a todas las personas que han hecho posible esta edición, al comité científico, a las diferentes áreas del instituto y a las empresas participantes en la zona de stands, y sobre todo a nuestras y nuestros estudiantes de posgrado, que son el corazón de este encuentro. Les invito a seguir construyendo juntos un Instituto Politécnico Nacional que a través del conocimiento transforme la vida de personas y contribuya al desarrollo de nuestro país. Por lo que para hacer la inauguración oficial del evento, les pido por favor se pongan de pie. Y siendo las 9:35, declaro formalmente inaugurado el Congreso Interpolitécnico 2025, agradeciendo su presencia y deseándoles una experiencia enriquecedora. Muchas gracias. Y bueno, desde este corazón inspirado y desde este momento les invito a entonar juntos la porra que nos llena de orgullo. Me toca por segunda vez dirigirla, así que creo que la segunda va a salir mejor que la primera. Y entonces, a la de 3. 1, 2, 3.
Buenum, buenum, gloria a la cachicachiporra, la cachicachiporra, pim pom porra, politécnico, politécnico, gloria.
Invitamos a nuestras autoridades a trasladarse a la primera fila para capturar la fotografía oficial del evento.
¿Me pueden ver esta cámara, por favor, con una sonrisa colgate? Aunque con José dijo que ya no. Por favor, para los demás. Bueno, de la cuenta de 3 vamos a cantar otra vez el vuelo, por favor. 1, 2, 3.
Buenum, buenum,
Gloria, la cachicachiporra,
la cachicachiporra, pim pom porra, politécnico, politécnico, gloria.
Gracias.
investigación para alumnos de posgrado 2025. Damos inicio con la primer conferencia magistral. Nuestra invitada y conferencista especial obtuvo su primer doctorado en PhD en 1978 y su segundo doctorado en Física y Matemáticas en 1991, con calificación Habilitation en el Instituto de Física de Semiconductores de la Academia Nacional de Ciencias, ambos en Kiev, Ucrania. Maestra en Física del Estado Sólido en la Universidad Técnica Nacional de Ucrania. En 1995 fue galardonada con el Premio Nacional de Ucrania en Ciencia y Tecnología. En 1998, las medallas Inventor de la URSS y 80 aniversario de la Academia Nacional de Ciencias de Ucrania. La doctora Tetyana es profesora de física en el Instituto Politécnico Nacional, autora de más de 400 artículos científicos con amplia experiencia en nanociencias y nanotecnologías relacionadas con la investigación óptica, eléctrica y fotoeléctrica de estructuras semiconductoras de baja dimensionalidad, pozos cuánticos, puntos cuánticos basados en materiales para el desarrollo de la física básica y aplicaciones de dichas estructuras en optoelectrónica, microelectrónica, biología y medicina. También es autora de las monografías Mecanismos de degradación de diodos, emisores de luz y láseres de semiconductores y nanocristales y puntos cuánticos de semiconductores del grupo cuarto. 22 capítulos de libros y 14 patentes utilizados en la industria electrónica la destacan. La doctora Tetyana tiene experiencia laboral en el Instituto de Física de Semiconductores de la Academia Nacional de Ciencias de Ucrania y en el Instituto Politécnico Nacional en México, y a la fecha es directora de 76 tesis del posgrado, 26 tesis de nivel doctorado en ciencias, 12 en Ucrania y 14 en México, y 50 tesis de nivel maestría en ciencias, 26 en Ucrania y 24 en México. Queda con ustedes y le damos una cordial bienvenida a la doctora Tetyana Torchynska, que nos hablará sobre algunos aspectos de los problemas científicos modernos en optoelectrónica. Un aplauso.
Buenos días a todos. I would like to inform you that I will make presentation in English because all my 400 publication is in English, terminology is in English. We have here the students of Posgrado, and students of Posgrado must understand English. Okay, my presentation is some aspect of modern physics in problem in optoelectronics. Optoelectronics, you could see around the around your life in any places. Optoelectronic, this is a display intelligent. This is a fantastic stellate. This is a solar cell and illumination. If some diode emits the light, it's optoelectronic. If some diode accepts the light, like solar cell, it's also optoelectronic. So we have seen optoelectronic in all our life, including this display of TV, including this display that you have seen here. So problems in modern problems in optoelectronic is very big list of this problem, and of course I could not talk about everything. I will talk mainly about the item what we investigate in our laboratory in Escuela Física y Matemática. modern scientific problem in optoelectronics. This is the intersection material science, quantum physics in device engineering. Mainly in SQL, we work with intersection material science and quantum physics. You could see here that main direction in optoelectronics connect with the creation more small devices, more fast working devices, low cost, low energy and low cost devices. And in this direction works 1,000 laboratories in the world. Today, I will talk about four directions, what we have, what we study in our school. The first direction connect with the quantum dots. Quantum dots, it's new particles, material particles, very small size, and these materials particles create a revolution in optoelectronics. I will say about that. Then we will say about quantum dots in different semiconductors devices. Mainly we work with the laser structures for optical fiber communication, so mainly I will talk about that. Then I will talk about Gaffney oxide and rare earth elements with Gaffney oxide and maybe I will talk about Gaffney oxide and rare earth element. Gaffney oxide is new material for optoelectronics. And finally, I will talk about zinc ore and alloys of zinc ore for transparent conducting oxide. And all of this item right now, this resolved modern problem in optoelectronics. No? Okay, we start with quantum dots. You could see here quantum dots. Quantum dots, it's very small part of material with a size like 210 nanometers, muy small. You could not see quantum dots in your eyes. Quantum dots needs to have another capping layer, to prevent electron recombine non-radiative. But this small quantum dots right now use in biology and medicine, quantum information in quantum computer, communication in telecommunication, machine vision, different cameras, display, illumination, in any place. Maybe you see in shops TV pantalla and have the primera letra Q and then lead, Q lead. Q lead, this is the quantum dots of different size that work in display of TV. Okay, but some knowledge about some knowledge about the quantum dot. Maybe you know that atoms have the energy level for electrons discrete. And this energy level, between this energy level, they have a forbidden band. As this is the atom discrete, when this atom accumulates in some solid state, this atom creates the band. And every material, every material, semiconductors, before 2000 year, it was bulk material, and they have banned the permission position for electrons and have forbidden band. But when the material decrease size, the size appears near to 10 nanometer, quantum confinement effect appears in these small particles. Quantum confinement effect possible explained on this figure. You could see here bulk material where electrons can move in any of three directions. You could see here quantum bells. Here only two directions is permitted for electron moving. You could see here quantum virus. Here only one direction permitted for electron moving. And you could see here quantum dots, when the electron needs to be directly in quantum dots and not permitted to move left, right, bajo, or arriba. So quantum dots have confinement around all surface of quantum dots. Right now, we start with quantum dots in biology and medicine. Biology quantum dots create in chemical reaction, create mainly core. Then this core is covered by barrier. This barrier has name confined barrier. We will talk a lot about the role of this barrier. And then this quantum dots covered of polymer for prevention, for some hermetization and prevention contact with humidity around the quantum dots. You could see here the structure, what have the quantum dots. Quantum dots have separate discrete energy level. Barrier is necessary for confinement electrons in conduction band and holes in valence band. You could see here one formula. I promise that it's only one formula in my presentation, but I need to say a lot about that. At the first, maybe in the end of 18, start 19, the Russian scientist Efros created theory of quantum dots. This theory includes only part, primary and second part. The first part is the band gap of the bulk material, and the second part is some addition to band gap in quantum confinement material. This addition, as you have seen, reverse proportional the size of quantum dots. So let us see this figure. If we change the size of quantum dots from 5 nanometers, for example, up to 2 nanometers for cadmium selenium material, the band gap increased, and together this increased band gap change the color of emission. Why we talk about emission color? Because why we talk about emission color? What is the emission in optoelectronic? I would like that you understand this because I a lot speak about band gap. But band gap is really is equal to quant energy, what emit electron in process of recombination. As a result, if we change band gap, we change quant energy. This is a quantum physics. You could see here process of emission. At the first, you could, using some laser, excite electrons from valence band to conduction band, and then these electrons recombine. This position, higher energy, this small energy, and difference electron emit as light, electromagnetic light, with a definite value of quant. So when we change the size of quantum dots, we change the distance between valence band and conduction band, and we change at the same time the value of quant, which can electrons in the process of recombination emit. So you could see here different color of quantum dots, and the difference in all these quantum dots connected only with the size. Much smaller or minus smaller. And what the second part of this equation was added later by scientific Bruce. He proposed to take in account Coulomb interaction between the electrons in hole. This Coulomb interaction with minus a little bit decrease the change of gap with change of the size. But nevertheless, effect continued to be, as I say, on the base of first edition part. Quantum dots in biology and medicine using for conjugation con different medical treatment for body, for human body. It's possible be the treatment, but it's possible to also be the antibody. Antibody conjugation, very important for diagnostic different inflammation in the body, different oncology tissue, or some another part of inflammation with the help of quantum dots. Here, I do not see if you have seen very clear. Here, different example, biological application of quantum dots, and you could see maybe different color. It's quantum dots used for visualization, a different part of issue. For example, vessels, or for blood vessels, lymph nodes, this lymph node, this blood vessel, different color for blood vessels red, for collagen blue. Thank you. And final picture, you could see here a mouse, and you could see quantum dots. These quantum dots were connected with antibody, prostata antibody. And when these quantum dots appear in vessel, they put directly to prostata and show inflammation in prostata. It's biological application. We will talk mainly about quantum dots on the base material 2,6. You could see here material what we used for quantum dots. For capping layer, we used zinc S, is also semiconductors materials. A core was quad-meselenium or cadmium-selenium tellure. With the change of size and also with the change of composition of material, we obtain different light. It's here you could see wavelengths in nanometers. Red is 605, 655, then near infrared, then 800 like infrared. This is our publication where we published our result. I will talk a small time mainly about our result. When the quantum dots start to use for bioconjugation, this process practically, it was not clear how bioconjugation influenced on luminescence of quantum dots. Because for biosensor, it's test influence of antibody a value of photoluminescence. And as a result, we investigate. We investigate interaction antibody with quantum dots and influence the antibody on photoluminescence spectra and also Raman spectra quantum dots. You could see here, for example, the quantum dots without bioconjugation. Then you could see here conjugation quantum dots to pseudo-rabbit virus. You could see that band shift in higher energy side, and you could see here the bioconjugation, luminescence with bioconjugation interleukin DS antibody. This shift is more significant. You could see here quantum dots conjugated again with pseudo-rabbit virus antibody, but this quantum dots is 800. This is the infrared quantum dots. In infrared quantum dots, blue spectra is without bioconjugation, red spectra is with bioconjugation. You could see here how change essential photoluminescence spectra when the bioconjugation processes will start. All this work necessary for calibration. Influence of quantum dots are photoluminescence spectra and Raman scattering. In this central figure, you could see Raman scattering spectra. Also, you could see that intensity, the Raman peak increased very much compared with the digitals 200, 300, and 800. Increased very in the process of bioconjugation. This effect have name safest enhanced Raman scattering. We investigate this phenomena, and we show that excited light stimulate formation electrical dipole in the body of antibody. This electrical dipole interact with quantum dots and lead to some decrease the size of quantum dots. Due to this decrease the size of quantum dots, the energy quant also change and shift in higher energy position. As a result, we right now make some conclusion relating to biological using of quantum dots. The safest enhanced Raman scattering effect was detected for very different antibody, very different quantum dots, and this effect connected with the generation electric dipoles in antibody that stimulate surface-enhanced Raman scattering. The photoluminescent spectra transformation in bioconjugated quantum dots is attributed to varying quantum confinement effect in core, as looks like electrical dipole shift electron from the surface and decrease effectively the size of quantum dots. And this effect stimulated by electromagnetic field of excited dipoles. This result obtained very important for understanding the process in bioconjugation and increase sensitivity of quantum dots as biological sensor. This study, our laboratory, was carried out with collaboration with University South Florida, Tampa, Estados Unidos. Right now, we pass to quantum dots in optoelectronic devices. I mentioned here laser emitting diodes, photodiodes, and solar cells. All these devices right now use the quantum dots, but mainly we will talk about laser structure because we work with light emitters for telecommunication and for optical fiber. Quantum dots in case of semiconductors devices is produced by molecular beam epitaxy. It grows in the chamber in higher vacuum. On some substrate, we use the quantum dots which grows Stransky-Krashtanov method. And you could see here not covered quantum dots on the on the surface of substrate. Why this quantum dots appears? We need to understand that layer which should produce quantum dots have parameter of crystal lattice personal. A substrate have parameter of crystal lattice nearly 7% different. Due to the mismatch, termed mismatch means different in parameters of crystal lattice between two contacting layers. Due to the mismatch, very great tension appears in material quantum dots. Due to the relaxation, the layer which originally was flat due to the relaxation, generate quantum dots in chamber in very high level of vacuum. After that, you could see here quantum dots without covering, but here, after that, before put the quantum dots outside the chamber, quantum dots covered by confining barrier. At the first, you could see here images of transmission electronic microscopy, and you could see buffer layer, quantum dots, and capping layer. It's possible to have one line of quantum dots, possible to have multi-line of quantum dots separated by barrier. Here you could see multi-structure, like sandwich structure, with quantum dots separated by barrier gallium arsenicum. Why quantum dots is important for optoelectronics? You could see here this picture that show you what parameters has laser structure, starting from 1970 up to 2005. This picture show you current, what will necessary to generate laser effect. And first laser have this current, 900 ampere per centimeter in quadrato. Created quantum wells, I say you quantum wells in first image. This current decreased up to 160 when created superlattice together with quantum wells. This current decreased to 90, but with quantum dots, this current decreased to only 6 ampere per centimeter quadrado. It's tremendous, dramatic change of current, what necessary for start laser effect. I say at the first that all work directed for low-cost energy for semiconductor devices. You could see here, really, quantum dots inside the laser structures permit receive very low current that necessary for light generation. Where quantum dots use also? I repeat that it's display in TV. It's mean QLED TV. It's laser. It's solar cells, and also quantum computing. Quantum dots can act as qubit for storing and processing information in quantum computer. Right now we talk a little about our work with this system. We start with a very simple system, gallium arsenicum buffer layer, indi arsenicum quantum dots. And we investigated 4 different compositions of indi gallium arsenicum capping layer. Influence this composition on the intensity of luminescence, the quantum dots. You could see here that composition, for example, 0.10, 0.15, not stimulate decreased intensity, but composition 0.20, 0.25 decreased essentially intensity the quantum dots. This I show energy diagram, and we create theoretical model for explanation this effect This model connected with the thermal escape of quantum dots, which provoked higher temperature, and due to this, intensity of quantum dots decreased. You could see here, rate, part of rate equation, which considered excitation processes in recombination processes. And these three rate equation were combined for understanding crucial part which influenced on quantum dots emission. And we show, finally, by the comparison numerical correlation with experimental data, that main role for decreased intensity of quantum dots play confinement barrier. Due to this, we start to work with different confinement barrier. But apart from confinement barrier, I could only edit some information about the needs, the laser for optical fiber. You could see here optical fiber transmission. And optical fiber not put any light on big distances. Optical fiber permit to put only 3 wavelengths. It's 850, 1310 nanometers, and 1550 nanometers. So only light with this wavelength could pass on very big distance. Optical fiber pass signal in 10 on 100 kilometers, and this signal should have just these 3 wavelengths. This is also very great limitation for creation laser structures. Here is the laser structure, what we investigated in 2005, 2010 years. And you could see that this structure is essentially complicated in comparison with the first structure, what we have. And this complicated structure include different way to increase intensity of luminescence during using confinement barrier, very high value. I show you our publication connected with different confinement barrier. We investigate alloys aluminium, gallium, arsenicum, aluminium, gallium, indium, arsenicum, aluminium, gallium, indium, arsenicum with different concentration of aluminium. And show you right now the final result. You could see here that aluminium, gallium, arsenicum create very big confinement barrier, 573. But due to difference in parameters of red crystallina, due to mismatch, what I mentioned, the interdiffusion gallium inside the indium arsenicum quantum dots change the emitting wavelength. And you could see here that emitting wavelength is 1180. We need, as you remember, 1300 for transmittance optical fiber. Then we use another confinement barrier. The result also not very nice. And only when you use another form, another composition of alloys in confinement barrier with higher percentage of aluminium, we receive emission, as you could see, just just corresponding transmission windows of optical fiber. And together with a higher barrier of confinement barrier near the quantum dots. This is a short conclusion concerning second part. We show that the confinement barrier, this composition with 40% alumina, permit receive intense ground state luminescence, receive wavelength length 1300 that necessary for second telecommunication windows, is small full width of emission band. This advantage for this material was received with, due to the higher binding energy of bonds, aluminium arsenicum, comparative with the gallium arsenicum and indium arsenicum bond. And due to the smaller concentration gradient India and Gallia, we include India in capping layer, we have the Gallia, include additional India in capping layer. And due to this smaller gradient, no introduce change the composition of quantum dots. This study was carried out in collaboration with Center of High Technology Material, University of New Mexico, Albuquerque, USA, because the equipment which necessary for produce such complicated structures, there is Albuquerque has, unfortunately, in our institute, we have not this equipment for production, such type of quantum dots and laser structures. Okay. The third direction of our investigation connected with the Gaffney oxide. You maybe know that mainly in semiconductors electronic using silicon oxide. Silicon oxide have very high temperature of crystallization, and due to this, different laboratory looking for the material with a little bit low temperature of crystallization, because this temperature influence on semiconductor dispositive devices inside of different semiconductors chip. We use hafnium oxide, interesting because this material have smaller band gap, 5.8, but transparent for all visible range. And due to this transparency, this is a very interesting matrix for rare earth atoms. Rare earth atoms being investigated like europium, neodymium, praseodymium. All these atoms create this separate level needed for optical sources and amplifier for optical fiber. In addition, rare earth atom, maybe you listen a lot right now about the problem United States and China, because China mainly produced rare earth atoms. In addition, the rare earth atom need for infrared spectral range light emitting diodes, for eye-safe sources, laser radar, medical, in different kind of surgery. So it's also very important modern items, very important modern items for investigation. You could see here our publication connected with this item. And right now, I present very short our result. Here you could see rare earth atom, praseodymium. As this atom have the electronic shell 4F, this electronic shell separate on different discrete level when this atom is put in matrix Gaffney oxide. And you could see here luminescence of different transition connected with the electronic recombination between levels of this levels, energy levels inside this atom rare earth. This effect looks like we discussed right now with quantum dots, where quantum dots also have discrete line, and quantum energy is a recombination between this discrete line. This rare earth atom is analog to quantum dots, and also light emitted in the process of recombination electrons in this energy levels. We investigated reasons of influence thermal annealing on the photoluminescence spectra and show that thermal annealing from one side up to the 1000 grams increased oxygen inside the Gaffney oxide. If the thermal annealing has the much more higher temperature, 1100, for example, the oxygen decreased. And also, for discrete separation of energy level in rare earths, we need crystal structure. We show here that with small temperature of annealing, no crystal structures appears. And in the same time, no luminescence of rare earth atom appears. But when the temperature was 1100, appears tetragonal crystal structure inside the Gaffney oxide. All in the same time appears photoluminescence of rare earth atoms. We investigated defects that participate in this photoluminescence. Rare earth atom has very small, you could see here, ds minus 18, ds minus 21 centimeter quadrature section for capture electrons. Due to this, energy, excitation energy appears in atom rare earth, they need help of some defect in the crystal lattice of the Gaffney oxide for excitation rare earth atom. You could see here the difference in luminescence spectra connected with the different defect structure. I say you that 1000 thermal annealing create materials with oxygen, with very high concentration oxygen. You could see here low energy photoluminescence band connected with a defect which is interstitial oxygen atom or molecules. But when the temperature increased, oxygen disappears and vacancy appears in the material, and photoluminescence spectra exchange very much. And low energy spectra disappear, a higher energy increased intensity. We propose the model that low energy light is excited by oxygen interstitial, a higher energy light is excited by excitation vacancy defect in Gaffney oxide. And we also show here how change intensity, low energy, all low energy band detected in the praseodymium atom with oxygen, and how appears the vacancy, decreased intensity, low energy because level the oxygen is low, a level of vacancies is higher. Due to this, when appears vacancies, higher energy band appears in spectra praseodymium atoms. Oh. This is also conclusion. Practically, I say everything what you could read here. Only I could add that this study was carried out in collaboration with some laboratory in France, in Caen University of France, and Institute of Semiconductor Physics at National Academy of Science, Kyiv, Ukraine. This is the final our investigation to talk today, connected with the transmission conducting oxide. Material what we investigated, it was zinc oxide and alloys of zinc oxide with magnesium. All climate changes right now, warming, and stimulate great attention to renewable energy sources, such solar cell and solar batteries. All this equipment, these devices, has as a front and back content transparent conduction oxide that need to push light inside p-n junction of solar cells. This transparent conduction oxide need have not only low absorption and higher transmission, but also need to have higher conductivity, because this at the same time electrode for devices. And for this, to increase conductivity, different doping impurities were used for this goal. But nevertheless, up to the moment when we start to investigate this material, the conductivity was low in comparison with conductivity of wide use material, such as ito. This is the oxide, indium oxide with stannum. So our task was increased conductivity of transmission conductive oxide. Before I continue, I would like to say that in semiconductors material, there is self-compensation effect. This self-compensation effect connected with the self-generation of defect when the concentration of impurity, which is especially introduced in material, is very high. This connected with the effect with higher tension of material due to difference in ionic radii, material matrix and material dopant, what introduced in matrix. So something like near the 10, 19, 10 21. This electron concentration which was possible to receive, and after this concentration of electrons in a transparent oxide, start the self-compensation process. So our task was shift the start of compensation process in area of higher intensity, in area of higher concentration. How it's possible to produce? We propose introduce in material donor impurities with low ionic radii 0.53 and big ionic radii 0.8 in comparison with zinc. So we expected that if we take much smaller ionic radii in donor impurity and much higher for compensation one or other, we could receive crystal lattice parameter just the same as has the zinc ore material without any donor impurity. Let us see what we received. You could see here SIMS images with layer what we investigated, and here you could see ADS spectra which show what really element there is in our structure. This is a zinc ore. You could see peak zinc, could see peak ore, and also you could see aluminium and indi peaks. So we have higher quality structure for investigation. I would like to say thanks to Dr. Bragim is Escuela UPITA, which have this technology to produce so very high quality layer. Okay. We investigated how change X parameter or X-ray diffraction lattice E calculated parameter. And you could see that with the increased aluminium concentration, we have constant indi concentration to dopant with different ionic radii. The lattice parameter of our film really change and pass directly to parameter of lattice which has the material without any doping, undoping material. So when we introduce atom low ion radii, big ion radii to compensate effect one and other, we practically avoid any stress, any residual stress in the film that initiate self-compensation process. And you could see this result. We calculated stress and show that for this definite concentration, stress practically change up to the very, very low level. Simultaneously, you could see here that for this concentration definite, photoluminescence increased dramatically because the crystal have not any tension and ideal crystal structure. And you could see here electrical characteristic. You could see here that when only indi was used, conduction was 10 minus dose. This is a 0.01 ohm multiplica per centimeter. Resistivity units, ohm multiplica per centimeter. But when we use two elements, indi and aluminium, our conduction was 10 minus 4. 10 minus 4. This is in 2 order big conductivity of film in comparison with doping the one element. And this conductivity, what I present here, this is a world record result for zinc ore. This practically what I would like, or not, it's important. This is the people who participated in our project from different schools of our institute. Physica and Mathematica, this is my school, and the doctor who works with me in this school. UPITA, this is also school, is the Institute of Politechnica Nacional. Esime Zakatenka and Esime Kolvakan. All doctors and maestros, the SS school participated in this project. Thank you for your attention.
Agradecemos la exitosa participación de la doctora Tetyana y a continuación el doctor Miguel Antonio Domínguez Crespo, coordinador del Comité de Organización, le hará entrega de un reconocimiento especial.
Bueno, pues muchísimas gracias por su excelente presentación. Espero que esto motive a nuestros estudiantes para seguir trabajando en el posgrado y con mucha orientación científica por parte de los asesores. Me voy a permitir, a nombre de la Secretaría de Investigación y Posgrado, le agradecemos mucho, doctora, y me voy a permitir leer este reconocimiento. Dice así: el Instituto Politécnico Nacional, a través de la Secretaría de Investigación y Posgrado, otorga la presente constancia a la doctora Tetyana Torchynska, ¿lo dije bien? Por su conferencia magistral con el tema Algunos aspectos de los problemas científicos modernos en optoelectrónica, en el marco del Congreso Intepolitécnico de Investigación para alumnos de posgrado. Ciudad de México, a 23 de septiembre de 2025. Doctora Marta Leticia Vázquez González, nuestra secretaria de Investigación y Posgrado. Muchas gracias. Aquí para que la... Muchísimas gracias y damos por terminada esta sesión. Los invitamos a que pasen a las conferencias ahora orales y que también nos acompañen a la sesión de los pósters, que va a estar dentro de este marco de las 11 a las 3 de la tarde. Muchas gracias a todos.